The AI-assisted generation of difficult math questions paper introduces a groundbreaking approach to automatically generate challenging math problems, leveraging recent advances in artificial intelligence and machine learning. The authors, Vedant Shah et al., aim to address the limitations of existing math question generation systems, which often produce simplistic or uninteresting problems. The paper highlights the importance of generating difficult math questions, which can help improve student engagement, critical thinking, and problem-solving skills. It notes that human-generated questions are often time-consuming and expensive to produce, while automated systems struggle to create problems that are both challenging and relevant. To address this challenge, the authors propose a hybrid approach that combines the strengths of machine learning and mathematical expertise. They introduce a novel framework, dubbed MathGen, which consists of three primary components: a math problem encoder, a difficulty predictor, and a question generator. The math problem encoder utilizes a graph neural network, GNN, to represent mathematical expressions as graphs, allowing the model to capture complex relationships between mathematical objects. The difficulty predictor employs a neural network to predict the difficulty of a given math problem, based on features extracted from the encoded graph representation. The question generator uses a combination of natural language processing, NLP, and mathematical reasoning to produce novel math questions. The authors propose a novel algorithm, called MathGen Search, which leverages the difficulty predictor to guide the search for challenging math problems. The paper presents a comprehensive evaluation of MathGen, using a dataset of over 10,000 math problems. The results demonstrate that MathGen can generate math questions that are both challenging and relevant, outperforming existing state-of-the-art systems. The authors also provide an analysis of the generated questions, highlighting the diversity and complexity of the problems produced by MathGen. The paper concludes by discussing the limitations of the current approach and outlining future work directions. The authors note that MathGen relies on a limited dataset of math problems and that expanding the dataset could further improve the system's performance. Additionally, they highlight the potential applications of MathGen in educational settings, such as personalized learning and adaptive assessment. Overall, the AI-assisted generation of difficult math questions paper presents a significant contribution to the field of math education and AI-assisted learning, offering a novel approach to generating challenging math problems that can engage and challenge students. The paper addresses the challenges in generating high-quality, diverse, and difficult math questions for evaluating large language models, LLMs. It highlights the dichotomy between human-generated questions, which are of high quality but not scalable, and LLM-generated questions, which are scalable but often lack the necessary difficulty and diversity. The authors propose an AI-assisted framework for generating difficult math questions by leveraging the understanding of mathematical skills possessed by top LLMs. This approach involves extracting core skills from existing datasets, such as the math dataset, and using these skills to generate novel questions that test a wide range of abilities. The generated questions are then reviewed and corrected by human annotators to ensure their quality and relevance. This framework has the potential to create more challenging and diverse evaluation datasets for LLMs, helping to address the issue of evaluation saturation and promoting deeper mathematical understanding in these models. A novel AI-assisted pipeline is presented for generating high-quality questions that require the application of multiple skills. The pipeline consists of 5 stages: skill pair validation, question generation, attempted solution, question validation, and final solution. Initially, the model validates a pair of skills to ensure they are distinct and not too similar. Then, it generates a question that necessitates the application of both skills for its solution. The model attempts a solution to the question using a defeatist approach and validates the question based on the attempted solution, checking for correctness, skill rigor, clarity, and other quality criteria. Finally, the model resolves valid questions using advanced techniques to enhance the accuracy of the final solution. The use of random pairs of skills drives improved diversity and difficulty among generated questions, requiring out-of-distribution thinking. This approach combines skills from 2 subareas, such as linking area and perimeter calculations with prime number knowledge. The resulting questions are challenging for both language models and human raters. The new dataset, MATH2, is significantly harder than the existing math dataset. Human experts play a crucial role in the AI-assisted process, refining generated questions to enhance their engagement value and providing gold standard answers. This collaboration boosts human productivity and results in high-quality, novel questions distinct from those in existing datasets. The work is connected to the concept of scalable oversight, which explores how humans might supervise and check AI systems that potentially outperform humans in many relevant skills. Human-AI collaboration could lead to more novel evaluations and introduce fresh perspectives into math instruction for AI and human learners. Figure 1 illustrates the AI-assisted pipeline, and examples of generated questions demonstrate the effectiveness of the approach. A comparison of the difficulty of the Math and Math2 datasets shows that the new dataset is significantly harder for all models. The authors highlight the importance of human-AI collaboration in generating high-quality questions that require the application of multiple skills, leading to improved diversity and difficulty among generated questions. The paper outlines a systematic approach to generating challenging mathematics questions by leveraging the capabilities of large language models, LLMs, and human expertise. It begins with skill extraction, where distinct mathematical skills are identified and cataloged from a dataset, creating a comprehensive evaluation framework. Next, the authors focus on generating questions that combine pairs of distinct skills to increase their difficulty. By utilizing advanced models like GPT-4 and Claude, and incorporating in-context examples of multi-way interactions between AI and humans, the model's performance in generating complex questions is enhanced. This step aims to produce challenging questions that robustly assess problem-solving abilities. The final step involves screening and validation to filter out invalid or flawed questions. This rigorous process includes evaluating and solving the questions to identify hidden flaws, such as computational intractability or logical inconsistencies. Advanced techniques like in-context exemplars and self-consistency further ensure the accuracy and quality of the solutions. This step is crucial for maintaining the integrity and reliability of the generated questions and their solutions. Overall, each step in the pipeline is designed to systematically enhance the quality and difficulty of questions, providing a robust and comprehensive evaluation of mathematical skills. The paper also includes a comparison of zero-shot chain of thought, COT, performance of various models on two different datasets, math and the generated dataset MATH2. Proprietary models exhibit the smallest decrease in performance, while smaller models within the same family experience more significant performance drops. The paper introduces a 5-step approach to generate challenging math questions using advanced models. This process is motivated by the challenges of creating high-quality, novel math questions that require the application of multiple skills. The approach employs a large language model, LLM, to validate skill pairs, generate questions, attempt solutions, validate questions against a fixed rubric, and obtain final solutions. Step 1 involves validating the skill pair by assessing their qualitative similarity. If the skills are deemed too similar, they are flagged and excluded from question generation. In Step 2, the LLM generates a question and a brief solution requiring the application of both skills in the sampled pair. The model is provided with 2 multiturn conversations between a human and an AI assistant to help anticipate and avoid practical issues. In Step 3, the model attempts a solution to the generated question, adopting an adversarial approach to identify flaws such as insufficient information, ambiguity, self-contradiction, or excessive computation. If any issues are found, the model stops solving and clearly states the problems. Otherwise, it completes the solution. Step 4 involves validating the generated question against a fixed rubric consisting of 7 criteria: single answer requirement, exact answer requirement, dual answer requirement, clarity and completeness, computational tractability, realism and logic, and syntax and grammar. The model uses reference examples and validation exemplars to facilitate this step and employs majority voting, MAJ at 4, to enhance robustness. For questions classified as valid, the LLM is asked to resolve the question to obtain a final solution in Step 5. Reference examples are provided in context to improve the model's understanding. Majority voting, MAJ at 4, is used to ensure consistency. If all the answers obtained in this step are unique, indicating potential ambiguity, the question is discarded. The questions obtained from the above pipeline are further screened by humans. This structured approach not only generates challenging and novel math questions but also ensures their quality through rigorous validation, effectively combining the strengths of AI and human oversight. The paper also presents experiments and findings, demonstrating the difficulty and quality of the Math2 dataset while analyzing the behavior of different models on this task of compositional generalization. The Math2 dataset is a challenging benchmark for evaluating the performance of language models on math problems, comprising 180 problems with 79 examples modified by human annotators to increase difficulty or correct errors. Modifications include changes to questions and solutions, with 41 questions and 62 solutions altered. This dataset is used to assess the performance of various language models, including MetaMath, Mammoth, Gemma, Llama 3, Phi3, DeepSeekMath, and Mixtral 8x7b Instruct. The experimental setup involves extracting skills from the math dataset using the pipeline proposed by Didolkar et al., 2024. These skills are then used to generate questions, which are verified and modified by human annotators, resulting in the Math2 dataset. The evaluation results, presented in Table 2, show the zero-shot performance of the language models on the Math2 dataset compared to the math test set. The results indicate significant drops in accuracy, with the GPT-4 Omni model showing a 13.42% drop and the Mammoth 7b model showing a 92.91% drop. These findings suggest that the Math2 dataset is a challenging benchmark for evaluating language model performance on math problems, requiring a deeper understanding of mathematical concepts. The dataset is designed to be more difficult and diverse than the math dataset, with a wider range of skills and topics covered. The evaluation highlights the limitations of current language models in solving math problems, with even the largest and most advanced models struggling to solve the problems in the Math2 dataset. This suggests significant room for improvement in this area. The Math2 dataset provides a comprehensive benchmark for evaluating language model performance on math problems, offering a foundation for future research in this area. The authors evaluate the performance of various large language models, including GPT-4 Omni, GPT-4 Turbo, Gemini 1.5 Pro, Claude 3.5 Sonnet, and Claude 3 Opus, on 2 datasets, Math and MATH2. MATH2 is a generated dataset that combines skills from different subareas of math, making it out of distribution, OOD, compared to the original math dataset. The results show that all tested models have significantly lower performance on Math2 than on math, with percentage drops ranging from 13.42% to 35.45% for frontier models. A linear relationship is discovered between the performance on Math2, y, and the square of the performance on math, x2, y approximately equals x2. This implies that the relative drop in performance is predictable from a model's performance on math alone, without considering its training details. The authors propose a heuristic explanation for this relationship, assuming that a model's performance on math reflects the average success rate of applying individual skills. On a random question requiring 2 skills, the probability of correct answering should be proportional to the product of the success rates of those skills, resulting in a quadratic relationship between the performance on math and MATH2. The findings suggest that the performance drop on MATH2 is not solely due to OOD issues but rather an inherent property of the model's skill composition. Open-source models, such as MetaMath and Mammoth, exhibit larger performance drops, likely due to overfitting to synthetic training data. In contrast, proprietary models of similar size show a more consistent pattern, with the relative drop in performance being predictable from their math performance. The evaluation uses the Mammoth evaluation suite for response generation, with a GPT-4 grader checking the correctness of solution responses against ground truth solutions. The temperature is set to 0, and top_p is set to 1 for all models. Additional details on compute resources and best fit quadratic curves are provided in Appendix A.3. The authors evaluate the effectiveness of their question generation pipeline in creating high-quality questions that require the application of multiple skills. They observe a relationship between the number of skills required and the performance difference between models, suggesting that the pipeline has created questions that genuinely require applying distinct skills. To further evaluate the quality of the generated questions, the authors test their effectiveness as in-context exemplars for the math dataset. They implement a new procedure to retrieve in-context exemplars from Math 2 based on the skill requirements of the current question. The results show that the generated questions outperform two baselines, demonstrating their effectiveness as in-context exemplars. The authors also analyze the distribution of skills in the Math 2 dataset, which contains 97 out of 114 skills extracted during the skill extraction process. They filter the math test set to remove examples requiring skills not present in the generated dataset, resulting in the removal of 809 test examples. The evaluation involves two experiments: a proposed four-shot COT, where in-context examples are used if a given skill is represented by fewer than 4 examples in Math 2, and b proposed plus skill-based four-shot COT, where additional exemplars are supplemented from the math training set. The results, presented in Table 3, show that the two prompting strategies using questions from Math 2 as in-context exemplars outperform the two baselines. This suggests that the generated questions are effective in-context exemplars due to their difficulty and skill relevance. The authors also discuss the limitations of their pipeline, including instances where models failed to follow instructions. They highlight the importance of human raters in improving the quality of the generated questions and explore intriguing behaviors of the models where they successfully create interesting and creative questions. The section concludes by emphasizing the potential of the question generation pipeline to create high-quality questions that require the application of multiple skills, and the importance of further refining the pipeline to improve its effectiveness. The authors present the results of their experiments on the math dataset, evaluating the performance of various models under different prompting strategies. Specifically, they compare the performance of models using Mammoth 4-shot COT prompting, skill-based 4-shot COT, proposed 4-shot COT, and proposed plus skill-based 4-shot COT. The results, as shown in Table 3, indicate that few-shot prompting with exemplars retrieved from the generated set of questions, Math 2, consistently outperforms vanilla few-shot prompting, with gains of up to 3.75% for Mixtral 8x7b instruct. The authors also analyze the creative questions generated by the models, which often failed to produce correct solutions but contained enough correct ideas for a human to quickly complete them. Human annotators verified the validity of the questions and the correctness of the solutions, suggesting changes to make the problems harder for automated tools to solve while allowing easier or more elegant solutions for humans. For example, an original question requiring recognition of the divisibility of k3 minus k equals k minus 1, k plus 1, by 2 and 3 was modified by a human rater to change the sequence size from 20 to 6 beads, maintaining the essential difficulty while making it more elegant for humans. All tested models failed on the modified question. The authors highlight the importance of human-AI interaction in generating creative questions and improving the quality of the questions. While the models frequently produced interesting and creative questions, they often failed to generate correct solutions. Human annotators played a crucial role in verifying the validity of the questions and the correctness of the solutions, and in suggesting changes to make the problems harder for automated tools to solve. The results demonstrate the potential of few-shot prompting with exemplars retrieved from the generated set of questions, Math 2, and the importance of human-AI interaction in generating creative questions and improving the quality of the questions. However, the authors also note the limitations of the models in generating correct solutions and the need for human annotators to verify the validity of the questions and the correctness of the solutions. Researchers emphasize the crucial role of human oversight in refining and improving mathematics questions generated by large language models, LLMs. To illustrate this, they provide examples of original questions created by LLMs, which are then modified by humans to increase their complexity and suitability for advanced mathematical problem-solving. For instance, a question about exponential growth and geometric series is revised to require understanding of underlying patterns, rather than mere computation. Similarly, a sequence defined recursively is modified to necessitate comprehension of the underlying pattern, rather than simple calculation. Another example involves a question about prime divisors, which is revised to require understanding of arithmetic modulo a prime, rather than brute force computation. The researchers categorized the failure modes of LLMs into 6 types, including insufficient involvement of skills, insufficient information, unsolvable or computationally intractable questions, nonsensical questions, deceitful solutions, and finding a needle in the haystack. Each type is accompanied by examples and explanations. For example, insufficient involvement of skills refers to questions that either omit one of the skills entirely or require a shallow application of one or both skills. Insufficient information refers to questions that lack essential details needed for solving, rendering them incomplete or ambiguous. The researchers propose a framework that leverages the complementary strengths of humans and AI to generate new, challenging mathematics questions. This framework utilizes LLMs to extract and name key skills necessary for solving math problems, and then employs these skills to generate questions that require advanced mathematical problem-solving. The discussion highlights the importance of human oversight in ensuring that the generated questions are of high quality and suitable for advanced mathematical problem-solving. The researchers also emphasize the need for further research to improve the performance of LLMs and develop more effective methods for generating challenging mathematics questions. A novel pipeline is proposed to generate math questions that combine pairs of skills from the math dataset, leveraging multiturn interactions with advanced large language models, LLMs. The pipeline's architecture involves employing named skills from the math dataset and utilizing LLMs to generate questions that combine pairs of skills. These questions are then reviewed and refined by human raters to ensure their quality and accuracy, resulting in a new math evaluation benchmark, MATH2. MATH2 assesses the same skills as the math dataset but is significantly more challenging for leading models. The pipeline's effectiveness is demonstrated by the improved performance of GPT-4o on the math dataset when provided with the newly generated questions as in-context examples. Notably, GPT-4t and GPT-4o exhibited the smallest performance drops on MATH2, aligning with the subjective evaluations of human raters. The results also show that providing the newly generated questions as in-context examples improved GPT-4o's performance on the math dataset more effectively than examples sourced directly from the math dataset. This finding validates the quality of the questions produced by the proposed pipeline. However, open-source models performed disappointingly on these new questions, suggesting that their performance should be improvable using novel questions of only moderate difficulty. The proposed pipeline can generate such questions at scale, making it a valuable tool for improving the performance of open-source math models. Nevertheless, the pipeline has limitations, including moderately high costs due to extensive API-based use of frontier models and significant human verification. Future work should focus on optimizing prompting strategies to produce higher quality questions initially, reducing the need for extensive filtering. Additionally, reducing human verification through the development of automated validation tools is crucial. The pipeline's potential applications extend beyond mathematics, enabling the efficient production of high-quality data in various domains. The research utilized compute resources provided by Mila and GPT-4 Access, as well as compute resources provided by Princeton Language and Intelligence, PLI. Recent advancements in large language models, LLMs, have led to significant breakthroughs in synthetic data creation, mathematical problem-solving, and multimodal understanding. Notably, Chan et al. 2024 have scaled synthetic data creation to 1 billion personas, while Chowdhury et al. 2023 have developed the PaLM model, achieving state-of-the-art results in various natural language processing tasks. LLMs have also demonstrated metacognitive capabilities in mathematical problem-solving, as explored by Didolkar et al. 2024. This research highlights the potential of LLMs to reason mathematically and solve complex problems, extending their capabilities beyond traditional language processing tasks. For instance, LLMs can learn to recognize and apply mathematical concepts, such as algebraic manipulations and geometric transformations, to solve problems. Targeted data generation with large language models, proposed by Gupta et al. 2023, aims to generate high-quality synthetic data for various purposes, including training and fine-tuning LLMs. This approach has the potential to improve the performance and robustness of LLMs in downstream tasks. The math dataset, introduced by Hendrycks et al. 2021, is designed to measure the mathematical problem-solving abilities of LLMs, providing a benchmark for evaluating their performance. Furthermore, researchers have explored the use of unnatural instructions for tuning language models, as described by Honovich et al. 2022, and keypoint-driven data synthesis for enhancing mathematical reasoning, proposed by Huang et al. 2024. These approaches aim to improve the mathematical reasoning capabilities of LLMs and enable them to solve complex problems more effectively. The development of LLMs has also led to significant advancements in multimodal understanding, enabling models to process and generate text, images, and other forms of data. This has far-reaching implications for various applications, including natural language processing, computer vision, and human-computer interaction. Overall, recent research has demonstrated the potential of LLMs to revolutionize various fields, from synthetic data creation and mathematical problem-solving to multimodal understanding and beyond. As LLMs continue to evolve, they are likely to have a profound impact on the development of artificial intelligence and its applications. Analyzing the quirks of the question generation pipeline reveals several failure modes of the models. One such mode is insufficient involvement of skills, where models generate questions that either miss one of the skills completely or require a shallow application of one skill while the other is sufficiently involved. This leads to potentially easy questions, defeating the purpose of skill composition. For instance, when combining the skills ratio _and proportion in geometry, Claude Opus generated a question that, although mathematically correct, did not require a rigorous application of both skills. The models also exhibit interesting behaviors throughout the pipeline, including creative questions generated by the models. Human annotators evaluated the questions based on their relevance to the skills being combined, the level of difficulty, and the clarity of the question. The authors provide details on the compute used for running their experiments and offer additional analysis of the model evaluations. The question generation pipeline involves multiple steps, including question generation, evaluation, and refinement. The authors provide examples of questions generated by different models in the question generation step, as well as a detailed description of the prompts used for each step. The models are evaluated based on their ability to generate questions that require a rigorous application of both skills. The authors also provide a link to the skill exemplar repository and in-context exemplars used in the question generation process. This section offers valuable insights into the strengths and weaknesses of the question generation pipeline and suggests future improvements. The analysis highlights the importance of careful evaluation and refinement of the generated questions to ensure that they meet the desired level of difficulty and skill composition. The experimental results demonstrate the potential of the question generation pipeline, but also reveal areas for improvement. The authors discuss the limitations of the current approach and suggest future work, including exploring alternative evaluation metrics and improving the robustness of the models. Overall, this section provides a detailed analysis of the question generation pipeline and its potential applications in educational settings. In the realm of generating high-quality questions that combine multiple skills, such as geometry and ratio _and proportions, several challenges arise. One significant issue is the insufficient information in generated questions, which can lead to unsolvable or computationally intractable problems. To address these issues, the authors propose solutions including multiturn human-AI interactions during the generation step and ensuring that the complexity of each skill application in the question being validated is similar to or more than the complexity of these skills in the reference examples present in the skill descriptions. Additionally, they suggest including an explicit clause in the question validation prompt to detect missing information and using a defeatist approach in the solution attempt step to identify flaws. In the realm of large language models, a significant challenge lies in generating high-quality, diverse, and relevant questions to assess their reasoning abilities. This task is fraught with three main issues: computational tractability, nonsensical questions, and deceitful solutions. To address these challenges, the authors propose a series of checks and validation steps aimed at filtering out problematic questions and ensuring that the generated queries are solvable, logical, and unambiguous. The first issue, computational tractability, arises when the complexity of generating questions exceeds the computational resources available. This can lead to an explosion in the number of possible questions, making it difficult to identify meaningful ones. To mitigate this, the authors suggest employing algorithms that prioritize question relevance and feasibility. Nonsensical questions pose another challenge. These are queries that do not make sense in the context of the task or are based on incorrect assumptions. For instance, asking a model to reason about a scenario that contradicts real-world physics would be nonsensical. The authors recommend implementing filters that detect and eliminate such questions by analyzing their semantic meaning and context. Deceitful solutions are perhaps the most insidious challenge. These occur when a model provides an answer that appears correct at first glance but is actually incorrect or irrelevant. For example, a model might respond to a question about the capital of France with Paris, Texas, which is technically correct but contextually wrong. To combat this, the authors propose using multiple validation steps to verify the accuracy and relevance of the generated questions and their corresponding answers. Through these measures, the authors aim to create a more robust framework for evaluating the reasoning abilities of large language models. By addressing the challenges of computational tractability, nonsensical questions, and deceitful solutions, they hope to generate high-quality questions that can effectively assess a model's capacity for logical reasoning and problem-solving. Designing effective validation prompts is crucial for large language models, LLMs, to generate questions that require the combination of two distinct skills. A well-structured prompt should include skill descriptions, validation exemplars, and conditions for the question. For instance, a prompt might ask the model to generate a question that requires the application of probability theory and number theory skills. However, LLMs often face challenges in maintaining focus and distinguishing between skills. To address these issues, the authors replaced referential terms with skill names, ensuring the model stays on track. A reasoning trace of the model's evaluation process reveals its ability to assess a given question against specific criteria, including single answer requirement, exact answer requirement, dual skill requirement, clarity and completeness, relevancy of information, and realism and logic. A sample question generated by the model involves calculating the probability of rolling a fair six-sided die 4 times and getting a product divisible by 36. The model's reasoning trace demonstrates its capacity to apply probability theory and number theory skills to arrive at the final answer. This example highlights the importance of careful prompt design to ensure LLMs generate questions that effectively test the desired skills. The model's ability to apply complex mathematical concepts to solve problems is a significant finding, showcasing its potential in various applications. However, the authors also emphasize potential pitfalls in prompt design, such as confusing skills or losing focus, which can lead to incorrect responses. By understanding these challenges and designing effective prompts, researchers can unlock the full potential of LLMs in generating high-quality questions that require the combination of multiple skills. The evaluation of a question validation model's performance in identifying and addressing various failure modes is crucial for ensuring the accuracy and reliability of the generated questions. Syntax and grammar play a significant role in this process, as they help to eliminate potential errors that could lead to invalid or nonsensical queries. In addition to these fundamental aspects, human verification is essential for double-checking the validity of both the questions and their corresponding solutions. This step not only improves the readability, quality, and difficulty of the content but also helps to identify any creative behaviors exhibited by the models. These creative behaviors can manifest in different ways, such as considering computational tractability or practical geometry during the validation process. By taking these factors into account, the models can generate more effective and relevant questions that better align with real-world scenarios and challenges. Overall, the interplay between syntax, grammar, human verification, and creative model behaviors is critical for developing a robust question validation model. This model can then be used to create high-quality, engaging, and challenging content for various applications, from educational materials to professional assessments. Analyzing the performance of various models on Math and Math 2 datasets reveals a quadratic relationship between their performance on generated questions and their performance on math, as illustrated in Figure 4a. This correlation arises from the fact that Math 2 questions require two skills simultaneously, whereas math questions require only one skill. A comparative bar plot in Figure 4b shows that smaller models generally exhibit larger performance degradation compared to their larger counterparts, with the exception of the Gemma family of models. This suggests that model size may be a factor in maintaining performance across different datasets. The modification of original questions to require deeper understanding and problem-solving skills is demonstrated through examples. For instance, the original question about finding the sum of the smallest and largest prime divisors of a number was reworded to find the sum of the two smallest prime divisors of a different number. This modification forces models to adopt a more analytical approach, rather than relying on brute force computation. The reworded questions require models to develop deeper problem-solving capabilities and adaptability across various datasets. The analysis highlights the importance of understanding underlying patterns and relationships in mathematical problems, rather than relying solely on computational power. The results emphasize the need for models to develop deeper problem-solving capabilities and adaptability across different datasets. The findings suggest that model size may play a role in maintaining performance across different datasets, and that smaller models may require additional modifications to achieve comparable performance to larger models. The distribution of skills in a generated set of questions reveals a non-uniform representation of 97 skills out of 114 extracted via the skill extraction process. Each question represents two skills, with some skills being represented by only one question. Experimental details include the use of two 80 GB A100 GPUs and 72 GB of RAM for open-source large language models, LLMs, and the evaluation of GPT-4 Omni and GPT-4 Turbo using 25 parallel workers, and Claude 3 Opus with 2 workers. Analysis of performance degradation on smaller models shows that they generally experience larger relative performance declines compared to larger models in the same family. This aligns with conclusions drawn in Arora and Goyal, 2023, Yu et al. 2023a, suggesting that larger models are better at composing skills or concepts, a phenomenon known as compositional generalization. This implies that larger models can more effectively combine skills to generate questions that require multiple skills. Examples of responses from different models, including GPT-4 Omni, Claude 3 Opus, Gemini 1.5 Pro, and Llama 370B Instruct and Llama 38B Instruct, demonstrate their ability to generate questions combining two different skills, such as area calculation skills and algebraic manipulation skills. These examples highlight the model's capacity for compositional generalization and their varying levels of success in generating questions that require multiple skills. The experimental results and analysis provide insights into the strengths and limitations of different models in generating questions that require multiple skills, and highlight the importance of compositional generalization in large language models. Calculating the area of triangle PQR, inscribed within rectangle ABCD, involves leveraging geometric principles and algebraic manipulation. Given the area of the rectangle is AB, the area of triangle PQR is specified as 1/6 of this value, expressed as AB6. To calculate the area using the coordinates of triangle PQR, we employ the formula for the area of a triangle with vertices at x1, y1, x2, y2, and x3, y3, given by 1/2 x1, y2 minus y3, plus x2, y3 minus y1, plus x3, y1 minus y2. Substituting the coordinates of p, 0, 0, q, a, kb, and r, Ka, B, into the formula yields the area of triangle PQR as 1/2, 0, KB minus B, plus A, B minus 0, plus Ka, 0 minus KB. Simplifying this expression, we arrive at the area of triangle PQR as 1/2 ab 1 minus k, which further simplifies to ab 2 1 minus k. Equating this to the given area of ab 6, we obtain the equation ab 2 1 minus k equals ab 6. Solving for k, we divide both sides by ab 2, resulting in 1 minus k equals 1/3. This yields two possible equations. 1 minus k equals 1/3 and 1 minus k equals minus 1/3. Solving these equations for k, we find two possible values for k, 2/3 and 4/3. This solution demonstrates the importance of precise calculation and attention to detail in solving geometric problems, highlighting the interplay between geometric principles and algebraic manipulation. In the context of geometric calculations and algebraic manipulation, a challenging problem is presented, involving an equilateral triangle ABC with side length 2a, and points D, E, F as the midpoints of sides BC, CA, AB respectively. The objective is to express the area of the shaded region, comprising the equilateral triangle DEF and squares ACDE, ABFG, BCHI, in the form Ka2, where k is a constant. The solution begins by calculating the area of equilateral triangle ABC as square root 3a2, utilizing the formula for the area of an equilateral triangle. Subsequently, the side length of equilateral triangle DEF is determined as square root 3a, leveraging the properties of midpoints and the 306,090 triangle. The area of DEF is then calculated as 3 square root 3/4 a2, applying the formula for the area of an equilateral triangle. Each square has a side length of 2a, resulting in a combined area of 12a2. Adding the areas of the equilateral triangle DEF and the squares yields the total area of the shaded region as 12 plus 3 square root 3/4 a2. The value of k is approximately 15.1981, obtained by evaluating the expression. This problem effectively assesses students' understanding of geometric calculations and algebraic manipulation, providing a visually engaging representation through the equilateral triangle and square constructions. The solution is straightforward to evaluate, making it suitable for assessing student performance in these areas. In a geometric problem involving an equilateral triangle and two circles, the objective is to determine the area of the smaller circle when the side length of the triangle is 4. The solution begins by identifying the centers of both circles, O for the larger circle and P for the smaller one. As O is the centroid of the equilateral triangle, the distance OC is calculated as 4 square root 3. Applying the Pythagorean theorem to right triangle POC yields a quadratic equation for the radius of the smaller circle, R. Solving this equation results in R equals 1 square root 3 plus 2 square root 10, 4. The area of the smaller circle is then calculated as pi r squared, simplifying to 27 pi 8 13 square root 3 pi 8 plus 5 square root 30 pi 4. A related problem involves finding the area of a shaded region formed by inscribing a square in a circle and drawing a semicircle inside the square. The solution requires calculating the area of the square and subtracting the area of the semicircle to determine the area of the shaded region. This problem tests both area calculation skills and algebraic manipulation skills. The page discusses a complex mathematical problem involving the calculation of the area of a region bounded by a curve and the z-axis. The curve in question is y equals x squared 4x plus 3, and the region of interest is between x equals 0 and x equals 2. To solve this problem, we need to integrate the function with respect to x, which results in an expression that simplifies to 2 square units when evaluated from x equals 0 to x equals 2. This problem tests both area calculation skills and algebraic manipulation skills, as it requires the student to find the area of a region bounded by a curve and the z-axis, and also to integrate a function with respect to x. The answer is not a simple numerical value, but rather an expression involving pi, adding an extra layer of complexity to the question. The skills of less than skill _1 greater than and less than skill _2 greater than exhibit distinct differences, despite both involving mathematical reasoning and problem solving. A closer examination reveals that less than skill underscore 1 greater than is primarily concerned with algebraic manipulations and solving equations, whereas less than skill underscore 2 greater than focuses on geometric calculations and spatial reasoning. Although they share some commonalities, these skills are distinct and require different types of mathematical knowledge and problem-solving strategies. In terms of mathematical reasoning, less than skill underscore 1 greater than involves the application of algebraic techniques to solve equations and manipulate mathematical expressions. This skill requires a strong understanding of algebraic structures and the ability to apply mathematical rules and formulas to solve problems. In contrast, less than skill underscore 2 greater than involves the use of geometric concepts and spatial reasoning to solve problems. This skill requires the ability to visualize and manipulate geometric shapes, as well as understand the relationships between different geometric objects. The differences between these skills are not merely superficial, but rather reflect fundamentally distinct approaches to mathematical problem-solving. While less than skill underscore 1 greater than is focused on the symbolic manipulation of mathematical expressions, less than skill underscore 2 greater than is concerned with the visual and spatial aspects of mathematics. As a result, these skills require different types of mathematical knowledge and problem-solving strategies, and are not interchangeable. In conclusion, the skills of less than skill underscore 1 greater than and less than skill underscore 2 greater than are distinct and require different types of mathematical knowledge and problem-solving strategies. Evaluating student performance in math exams requires a nuanced approach, particularly when assessing analytical and mathematical reasoning abilities. Two essential skills, algebraic manipulation and geometric reasoning, are critical in solving complex problems that demand expertise in both areas. To accurately evaluate student proficiency, exams must be designed to test these skills simultaneously, without the aid of computational devices. A key aspect of this evaluation process involves presenting students with questions that necessitate the application of algebraic manipulation and geometric reasoning in tandem. However, the development of such questions poses significant challenges. For instance, a conversation between two agents, Agent A and Agent B, highlights the complexity of creating questions that effectively assess these skills. While the context of this conversation is unclear, it underscores the importance of careful question design. An attempted solution to a sample question, intended to evaluate analytical and mathematical reasoning abilities, reveals potential flaws in the question's construction. The solution's defeatist approach suggests that the question may be unsolvable, self-contradictory, computationally intractable, ambiguous, or open to multiple interpretations. This emphasizes the need for rigorous question validation to ensure that assessments accurately evaluate student expertise in algebraic manipulation and geometric reasoning. Effective question validation involves crafting precise and unambiguous questions that avoid unnecessary complications. This process is crucial in preventing confusion, approximations, or rounding errors that can compromise the validity of the evaluation. By prioritizing clear and well-defined questions, educators can create assessments that accurately measure student proficiency in these critical mathematical skills. Evaluating student performance relies heavily on the quality of assessment questions. To ensure that questions effectively measure student abilities, several criteria must be met. A high-quality question should require a single answer, an exact answer, and the simultaneous application of two skills. Additionally, the question should be clear and complete, computationally tractable, and relevant to the information being assessed. Realism and logic are also crucial, as is proper syntax and grammar. Assessing whether a question meets these criteria can be challenging. For instance, evaluating a question's ability to test the simultaneous application of two skills requires careful consideration. This involves analyzing the question's language, structure, and content to determine whether it adequately assesses both skills. Sample conversations and examples of skills can help illustrate potential difficulties in this task. One key consideration is the dual skill requirement. A question that requires the application of two skills should be designed to assess both skills simultaneously, rather than sequentially. This can be achieved by crafting questions that integrate multiple concepts or require students to apply different skills in a single response. Another important aspect is computational tractability. Questions should be designed to be solvable within a reasonable timeframe, taking into account the student's prior knowledge and skills. This ensures that the question is assessing the student's abilities, rather than their ability to perform complex calculations under time pressure. By carefully evaluating questions against these criteria, educators can create high-quality assessments that effectively measure student performance and provide valuable insights into their abilities. This research demonstrates the application of two fundamental mathematical skills, Skill 1 and Skill 2, through a series of question-answer pairs and conversations. The questions and answers are designed to test the ability to reason and solve problems using these skills. Skill 1 is exemplified through questions such as determining the maximum value of a quadratic function, finding the equation of a line given 2 points, and calculating the area of a triangle. Corresponding answers provide step-by-step solutions to these problems, illustrating the application of Skill 1. Similarly, Skill 2 is demonstrated through 3 question-answer pairs, showcasing its application in solving problems related to geometric transformations, algebraic manipulations, and numerical computations. The page also presents 6 conversations, labeled as Conversation 1 to Conversation 6, which serve as validation exemplars. These conversations assess the ability to engage in mathematical discussions and reason about problems. A question is then presented, along with a solution attempt, but this solution is not utilized in the final solution. Instead, the final solution leverages in-context exemplars from the math dataset, designed to evaluate mathematical reasoning abilities. The prompt for the final solution provides a brief description of the 2 mathematical skills, followed by the same question-answer pairs presented earlier. This approach suggests that the authors are using external resources to evaluate the mathematical reasoning abilities of a model or system. By providing a prompt that includes the skills and question-answer pairs, the authors aim to assess the ability to reason and solve problems using these skills. The use of in-context exemplars from the math dataset indicates an attempt to leverage external resources to support the evaluation process. This approach allows for a more comprehensive assessment of mathematical reasoning abilities, as it draws upon a diverse range of problems and solutions. Overall, this research presents a series of mathematical problems and conversations designed to evaluate reasoning and problem-solving abilities, with a focus on leveraging external resources to support the evaluation process. Evaluating a student's math exam solution requires a comprehensive assessment of their thought process and methodology. The task involves comparing the student's solution to the correct solution, considering each step in detail. This process entails not only verifying the final answer but also understanding the reasoning and approach used by the student. A structured evaluation approach is essential, comprising 2 key components: a step-by-step explanation of the thought process and a final correctness assessment. The step-by-step explanation should detail the evaluation process, highlighting any discrepancies or similarities between the students and correct solutions. This involves analyzing the student's work, identifying any errors or misconceptions, and understanding the underlying reasoning. The correctness assessment should provide a clear and concise statement of whether the student's solution is correct or not, without additional commentary. This evaluation process is crucial for understanding the student's grasp of mathematical concepts and their ability to apply them to solve problems. By adopting this structured evaluation approach, teachers can identify areas where students may need additional support or practice, ultimately enhancing their learning experience and academic performance. This comprehensive evaluation process enables teachers to provide targeted feedback and guidance, helping students to improve their problem-solving skills and mathematical understanding. The evaluation process is not only focused on the final answer but also on the student's thought process and methodology. By examining the student's work in detail, teachers can gain valuable insights into their understanding of mathematical concepts and their ability to apply them to solve problems. This information can be used to inform instruction and provide targeted support to students, helping to improve their academic performance and mathematical literacy.